Every day, firefighters all over the country risk their own lives to help save other people's lives and property. But at the end of the day, they need to be able to return home to their own families.
The issue we want to focus on is what if they run into trouble on duty? How will the other firefighters find them?
What about GPS? I know exactly where I am.
Well, that's great for you, but how am I going to figure out where you are?
And a GPS signal is only accurate to about 10 feet in ideal conditions.
And it doesn't go through buildings very well either.
But I know where I am.
I was watching on TV where they were tracking wolves with directional antennas.
The problem with that is that it would require 2 antennas constantly moving to track one firefighter.
And firefighters never work alone. We need to be able to track all of them.
My phone uses signals from cell towers to find my position.
Yeah, but cell towers aren't always available, and in an emergency, they could even be affected.
I saw on a TV show where they were able to track somebody by his heartbeat.
Pretty sure that was on Star Trek.
Yeah, that doesn't exist. Hello, we are the Tinkers, and for Senior Design 2015, we have the privilege of working on the Firefighter Tracker, sponsored by Active 911.
My name is McKay Lindsay, and I did the PCB design and layout, embedded system design. I populated the boards and did much of the embedded programming.
My name is Leanne Sherry, and I did RF circuit design, signal processing, and the GUI design and programming.
My name is Ingrid Udd. I worked on transmission line effects, administrative tasks, and PCB schematic and layout validation. What we propose is to use an active radio signal sent from each individual firefighter to a central location and use this information to triangulate their location.
Triangulation is if we know the distance from one of our base station antennas to the person, we know where he is on this arc. And with 2 antennas, and a little bit of trigonometry, we can figure out exactly where he is. And if we want to find him in 3 dimensions, all it takes is 1 more antenna at a different height from the other 2. Our block diagram is broken into 2 main parts, the mobile unit and the base station unit. Both of these are built on a foundation of the BeagleBone Black, which is a small computer running Linux that also has breakout pins like a microcontroller. The rest of our hardware was built into a cape which attaches to the BeagleBone, and the only differences between the mobile unit and stationary unit is that there is hardware attached to the stationary that was just left off of the mobile unit. The BeagleBone was chosen as our platform because of its ability to use Python for programming, and there are already libraries available for programming all of the specific needs on our board, such as SPI, I2C, and the ADC, or analog to digital converters. The transceiver is a device that acts as both a transmitter and receiver. We can program it to transmit at a variety of frequencies. It is used for the 2-way data communication and to transmit the signals we use in our analysis in other blocks.
The antenna in this system was chosen based on the datasheet for the initial transceiver chosen for this project. We ended up using the next generation of the transceiver, but the purpose of the antenna didn't change. Because the transceiver is a very low-powered chip, a 1/4 wavelength monopole antenna was recommended. It is a resonator for radio frequencies and is compact compared to other types of antennas. But due to its design, this antenna has a gain of 1.1 dBi, which helps maintain measurable signal strengths at the required distances.
The filter block filters out the high-frequency information from the onboard signal coming from the signal hardware. It's a simple single-pole RC filter. The signal hardware block was used to change the signal from a radio frequency to a signal that can be processed by a computer. It includes multiple stages of signal processing. The output will be refined in other blocks. The BeagleBone programming block is used to program the signal hardware and runs on the BeagleBone Black. It programs the signal hardware with I2C and bit toggling. The programming also includes ADC programming to grab the information about the signal from the signal hardware. The signal programming block was used to extract vital information from the signal that was manipulated in the signal hardware block. The extracted information is sent to the distance programming block.
Signal hardware and signal programming output values that are then taken into the distance programming block. This block takes those values and uses MATLAB, a high-level scripting language, to produce a distance. Using consecutive values from the signal hardware and signal programming blocks, the multiple distances required for triangulation are generated.
The next block is the GUI output. The GUI was programmed in Qt, a C++ GUI program. It displays a visual representation of where two firefighters are every second. It takes coordinates as an input and outputs visually where they are every second. Commanding officers can then use this information to determine what to do.
The LCD display block is used to demonstrate bidirectional communication. I2C, a two-wire interface communication protocol, is used to transfer information from the BeagleBone to the display, and the messages sent by RF from the mobile unit to the base station are easily read on the screen.
The bar graph block consists of an array of LEDs that have multiple uses depending on the need. They have been used to display the RSSI, or Received Signal Strength Indicator. They can be used to indicate the frequency we are transmitting or receiving on, or just as a general indicator light.
The buttons on the mobile unit and base station are used to transmit bidirectional data. For the purposes of the prototype, 3 buttons were implemented so that multiple messages could be verified, and during testing, variations of the transmitting protocol were easy to switch between.
The mobile programming block is actually programming that is used on both the mobile and stationary units. It consists of a Python program with its associated libraries to program the transceiver, the LCD display, the bar graph, and the buttons. It uses the established Linux library for the I2C protocol used in programming the LCD display, and the Adafruit library for the SPI protocol used to program the transceiver.
For the mobile enclosure block, it is essential that the system is light and easily carried around so as to not impede the work done by the firefighter wearing the device. The case for the prototype is clear so that during testing, the team was able to visually inspect the LED bar graph and manipulate the buttons.
The base enclosure was made out of a purchased black plastic box. Holes and a slot were dremelled so that the base station could fit inside with access to all necessary ports. A BeagleBone and a battery needed to fit inside. The antenna needed to stick out, and access to the mini USB port on the BeagleBone was necessary.
System requirements are essential for this project in order to hold ourselves to a certain standard. Determining these system requirements determined the path the project took.
Our first system requirement was to have a user interface so that the base station can tell where all the firefighters are at a given time.
Our second system requirement was to uphold the FCC safety regulations so that nobody coming into contact with our system would be injured.
Our third requirement was to design a receiver that could receive the signals for multiple firefighters being tracked.
Our fourth requirement was to be able to run continuously for 2 hours. We didn't want the firefighters to have to recharge in the middle of fighting a fire.
Similarly, we didn't want the firefighters to be constricted by the weight of their system, so we determined that it should be as light as possible.
We also determined that in order to make this a self-contained system that we needed to use RF or radio frequencies to be able to track the firefighters.
Our next system requirement was to be able to track to an accuracy of 50 centimeters.
In order to do this, we had to have a system that supports multiple frequencies.
We also needed to be able to transmit these frequencies at a power sufficient enough that it could go through walls and that it could be measured at a minimum distance of 30 meters away.
Our last system requirement was to be able to have two-way communication. This way, the base station and the firefighter could communicate via text displayed on the screen.
Because firefighters will need to be able to use this system in a variety of environments and circumstances, we needed to ensure that the entire system was self-contained. For this reason, we chose an RF-based system that would have transceivers, or chips that can both transmit and receive the signals, on both the firefighters and at the base station outside of the building. Besides being able to track the firefighters, this gave the added benefit of being able to have two-way communication.
Even when the two-way communication isn't happening, there's still RF signals being transmitted.
Given the information out of the signal hardware processing Leanne just described, that information is then taken and analyzed in software. And through software analysis, eventually find the distance between nodes A and C and A and D.